Hello everyone. In this video we are going to learn about the statements of second law of thermodynamics. Okay, so in my previous video of second law of thermodynamics I had discussed about the usefulness of second law. Why do we need second law? And there are some limitations of first law due to which that is overcome by the second law of thermodynamics. In this video I am going to discuss the statements. So there is no particular statement, there are mainly two statements, Clausius and Kelvin-Planck statements. So in this video I'll discuss these two statements and what they mean and what they actually say about the second law. So there are mainly two statements, one is Clausius, other one is Kelvin-Planck statement. Let's first discuss the Clausius statement. So what Clausius says is that it is impossible for any system to operate in such a way that the sole result would be an energy transfer by heat from a cooler to a hotter body. So in this statement there are three important things. First thing is the sole result. Okay, we'll understand what is meant by this sole result. Second thing, the transfer of heat. Okay, and the third thing which we have to remember is that the heat is getting transferred from a cooler to a hotter body. Okay, so let's understand this statement using this example. So there is one body which is having a temperature th. H is for hot and c is for cold. Okay, so this is having a lower temperature, this is having a higher temperature. So from your regular experience you know that the heat will be transferred if you bring these two body in contact. Heat will be transferred from hotter body to a cooler body, right? It will not transfer automatically from a cooler body to a hotter body. So this is not possible. Okay, this is possible and this is not possible, as we all know from our regular experience. Then what Clausius says is that it is impossible. So it is impossible to transfer heat from a cooler body to a hotter body. If it is not just this, if that is the sole result, what is meant by this sole result means it is not the only process happening. Okay, if there is some other process also happening with the transfer of heat, then it is applicable. Okay, then it is possible. Okay, only when this process is happening, transfer of heat from a cooler to a hotter body, that is impossible. Okay, let's understand with the help of a refrigerator. Now what happens in a refrigerator? You keep, even if you keep the chilled item, the items inside the refrigerator are having a lower temperature than the surrounding. For example, this is at 5 degrees Celsius and outside temperature is 25 degrees Celsius. So what this refrigerator does, takes heat from the low temperature body and rejects heat to the high temperature surrounding. So it is taking heat from the 5 degrees Celsius and transferring it to the 25 degrees Celsius surrounding. So that means the heat is transferred from a cooler body to hotter body in case of a refrigerator. But it is not the sole result, means this is not the only process happening in the refrigerator. So if in case of, you might have heard, there is a black color box in the refrigerator at the bottom side. That black color box is a compressor where you actually transfer some amount of work in the refrigerator. So that is not the sole result. So if that is the sole result, that is not possible. This is the second law of thermodynamics. The clause is a statement of second law of thermodynamics. So I hope this statement is clear. Now we will discuss the Kelvin-Planck statement. Okay, now let's understand the Kelvin-Planck statement. Okay, so what Kelvin-Planck statement says that it is impossible for any system to operate in a thermodynamic cycle and deliver a net amount of energy by work to its surrounding while receiving energy by heat transfer from a single thermal reservoir. So here these three terms are very important. First is that the system should operate in a thermodynamic cycle. So let's understand what is meant by thermodynamic cycle. Okay, so in thermodynamic cycle there will be sequence of processes. Okay, let's say we started from this point 1, then we move to some other, there is one process, we move to 2, then 3, like that. Okay, this is point number 3. Now this is third state, and then finally again we reach to the point number 1. So when the initial and the end state, or the from where we started and the final state where we reach, if these 2 points are same, then we say that this system is operating in a thermodynamic cycle. Okay, there are various examples of system operating in a thermodynamic cycle. One example is that power plant. Okay, the thermal power plant. They work on a thermodynamic cycle. So the start point and end point are going to be the same. So if a system operates in a thermodynamic cycle, then what happens? And it is delivering a net amount of work to the surrounding. So work is delivered to the surrounding. Okay, this is an important thing, and it is only receiving energy in the form of heat from a single thermal reservoir. Okay, if a system is doing like this, that is impossible. This is what is the Kelvin-Planck statement. Okay, so now let's understand this using this figure. Now here there is one system, this is my system, which is operating in a thermodynamic cycle. Okay, and this is one thermal reservoir which is having a temperature T and it is giving some work output. Okay, so from the Kelvin-Planck statement, this is not possible. A system cannot operate on a single thermal reservoir and deliver net amount of work to the surrounding. Now, there is another thing. Let's see this figure. In this figure, the system is operating in again with a single thermal reservoir. This is operating in a thermodynamic cycle, and it is exchanging heat with a single thermal reservoir. And in this case also there is a work transfer involved. So do you think in the second figure, this is possible from Kelvin-Planck statement? Yes, this is possible from Kelvin-Planck statement. And what is the difference as compared to the first figure? If I compare first and second figure, what is the difference? In first figure, the system is delivering work to the surrounding. Okay, so work is going out. In this case, work is supplied to the system. Okay, so work is supplied to the system. So in Kelvin-Planck statement, it is clearly mentioned that there should be net work transfer to the surrounding. Okay, so if the system is getting work, if the work is done on the system, that is possible from the Kelvin-Planck statement. Okay, and there is another figure. In this figure, what is happening? There are two thermal reservoirs. Okay, so one is that having a temperature T, maybe you can call it a TH and TC. Okay, they are having different temperatures. One is at high temperature, one is at low temperature. Okay, now T cold and T hot. So in this case, they are operating in two thermal reservoirs. Okay, and there is a net work output from the system. Okay, so this is also possible from the Kelvin-Planck statement, because in this case, what we are doing, instead of single thermal reservoir, there are two thermal reservoir. So this is also possible from the Kelvin-Planck statement. So only first case is not possible from the so only first case is not possible. All other two cases are possible from the Kelvin-Planck statement. So I think the Kelvin-Planck statement is clear to you. So both the statement, the Kelvin-Planck statement and Clausius statement are equivalent to each other. If you don't follow one, then other will be violated automatically. Okay, so these are the two statements of second law of thermodynamics. I hope you have understood